Hey everybody, this video is going to be the first in a series of videos about how you read the notation for limits in calculus and how you can use graphs or tables to estimate the limit of a function as it approaches a particular value. So here these are some skills and objectives that we would typically have for our calculus class. Feel free to pause and read over these if you want. But let's go ahead and get into what we're looking at for limits and how you define them or how you notate them. So a limit is an old concept that was part of the process that people would go through on the way to what Newton and Leibniz did for finalizing what they did for calculus. But the idea of a limit is just as a number approaches, or as a function approaches a number. How does the function behave? What does it approach? And you've seen some of this stuff in pre-cal or college algebra, and this is how you're going to take those concepts and apply them in a calculus setting. So we have three basic types of limits. We have a left-hand limit, a right-hand limit, and a general limit. And the way that we notate the difference between a right-hand limit and a left-hand limit is the notation that we have here. So if you notice, we have LIM, for the abbreviation for limit, and some generic function f. And we're saying x is going to approach some number, which we're just generically calling c. And that positive, that symbol, the plus sign in the top where the exponent is, that's just simply saying that we're going to approach that number from the right side of the graph, or the right side of a number line. And this is how we would read that calculus notation. The limit of a function f as x approaches c from the right. So the left-hand limit is going to look essentially the same thing, except in the exponent spot on our generic number c that we have in this case is a negative symbol, indicating that we're going to approach c from the left-hand side of the graph. And that's what we have here. So the general limit is simply going to be the limit of f as x approaches the number c, whatever c happens to be. And we're not looking at necessarily a particular direction. This might be something that you will use to indicate with general substitution that how you want to evaluate it. But those are the three ways of noting a limit in calculus: left hand, right hand, and general limits. So moving on here, we're going to use a concept from pre-calculus, in this case a rational function, and see how can we look at it and evaluate it so that way we can start looking at its behavior. So what I'd like you to do is take the function that's been given to you. Function f has a second degree polynomial in the numerator and the denominator. And I'd like you to go ahead and, in your notes, just go ahead and try doing these things. Can you factor and simplify the function? Identify where the holes, if there are any, what's the domain and range, and where the asymptotes are. So go ahead and pause the video and attempt to do that now. And when you're ready, go ahead and hit play and check your stuff with mine. All right. So hopefully you've factored the polynomial, or not the polynomial, but the rational function. So when you factor the numerator and the denominator, you are going to see that it has a common term of x minus 3 that will be simplified out of the general equation, giving us a simplified rational expression of 3x plus 1 over x plus 3. Because it does have a common factor in the numerator and the denominator, it does have a hole at x is equal to 3, because that's the factor, that's the solution that we get when we set that factor equal to 0. Taking the 3 and substituting it into the basic or the simplified expression gives us our hole at 3 and 5/3, or 3 and 1 and 2/3, however you want to think of it. And the domain, you can look at the graph as it's given to you and write out the domain. Otherwise, you can kind of look at the function itself and say, well, I have a hole at 3 and 5/3, so that can't be part of the domain. And I also have a vertical asymptote at x is equal to negative 3 based off of the remaining expression that I have in the denominator. That's where my vertical asymptote comes from. And so we have a domain of everything except, so from negative infinity up to the negative 3, from the negative 3 to the positive 3, and from the positive 3 to positive infinity. And the range is going to be fairly similar. When you look at that, it's going to have a range. If you start at the bottom of the graph and work your way up, well, we still have to exclude the y value of our whole, so we're going to take that 5/3 out. So from negative infinity up to 5/3, but we go from 5/3 to 3, and then finally from 3 to positive infinity. The vertical asymptote comes from the remaining factor in the denominator, which was solving that gives me x is equal to negative 3 for the vertical asymptote and the horizontal asymptote. If you recall from your pre-cal information, this is a balanced function, so if I look at the ratio of the leading terms, I compare those and I get a horizontal asymptote at y is equal to 3. So now what we're going to do is we're going to take that basic function and we're going to try to evaluate the graph using the notation. So here you can kind of look in your notes if you have it. You can see where the graph is. Here I'm giving myself a little graph to kind of refer to. But again, go ahead and pause the video and try to fill in the blanks here for what's going to happen when you evaluate the function, and when you're ready, hit play again and check your values with mine. Alright, hopefully you've gone ahead and paused the video and got your blanks filled in. So we read I'm starting the top row, and it says as x approaches negative infinity, the graph is going to approach something else. So if we look at the graph, as x goes towards negative infinity, we're going this way. We see we're getting closer and closer to the horizontal asymptote at 3. As I go, let me go ahead and change colors. As I go from we're still in the top row, as I go towards positive infinity, what happens to the function? So as I go towards positive infinity, again, I'm going to approach the horizontal asymptote at 3. As x approaches 3 from the left-hand side, as x approaches 3 from the right, negative 3 from the right, what does y do? So as I approach negative 3 from the right, you can see as I get closer and closer to negative 3, the graph is going down towards negative infinity. As I approach positive 3 from the left, well, positive 3 from the left is hard to do. I can't really do it from the far left, because if you notice, if I do it from the far left, I go up towards positive infinity, so that one doesn't really work. But if I approach positive 3 from the left-hand side, I will be doing it here. And what happens is I approach that whole 5/3. Okay, moving on to the bottom row, as x approaches negative 3 from the left, what happens to the graph? Well, you can see as we approach negative 3 from the left-hand side, and let me pick another color. As x goes towards negative 3 from the left-hand side, you can see the function is bending up, going towards positive infinity. And finally, as x approaches 3 from the right-hand side of the graph, what does y do? And as it approaches positive 3 from the right side, it again is going to approach where that hole is at 5/3. So we're just looking at the graph and interpreting where it goes. And finally, down here at the bottom, can you explain the value of a limit represents in terms of the graph? In this case, this is what my explanation was. The limit is the y value that the graph is approaching from both the left and the right sides of the target value, whatever c happens to be. And the limit can occur at a hole, which is otherwise known as a removable discontinuity. So we're going to go ahead and pause the video here and pick it up with the second video soon for the next part of our notes. If you have any questions on anything that you've seen so far, by all means, let me know. But until then, thanks for watching. Take care.